Okay, we're back, and we're going to look at 8.2, probability, the addition principle, and complements, and we're going to try and use these lines on the page to keep my handwriting in check. So we will start with some definitions. In this video, we'll start with definitions, which will include looking at problems 25 and 26. We'll talk a little bit about Venn diagrams and probability. And so that will deal with problems 1 through 6 and 71 through 74. Some more card problems. Problems 7 through 18 and 53 through 56. And then some dice problems, right? Card problems and rolling 2 dice are sort of classic examples of probability. And it's problems 27 through 30. And then some, what do they call this? Quality control problems. So these are the word problems. So quality control, that's a Y. Word problems. And that's problems 75 and 76. Okay, and most of this is about the addition principle and complements and how that affects probabilities. Okay, so first a little definitions. So addition principle. And probabilities. So we'll set S to be our sample space, and E, F are 2 events. So E is a subset of S and F is a subset of S. Right? Sample space, this is all stuff that can possibly happen. E is some of the stuff that can happen. F is some other stuff that can happen. And we know from chapter 7 that the addition principle is this. The number of things in E union F is the number of things in E plus the number of things in F minus the number of things in the intersection, right? Because you don't want to double count the intersection. But remember that union is usually or, intersection is usually and. So if we're thinking about this in terms of letters and events, either the number of ways that either E or F can happen is the number of ways that E can happen plus the number of ways F can happen, that's an F, minus the number of ways that E and F can happen. Okay, so what's the probability then? What's the probability of E or F? Right, the probability of that. Well, probability is the number of ways the thing you want to happen divided by the number of things that can happen. And N of S, that's the number of things in the sample space. So N of E or F, that's all this stuff here. So it's N of E plus N of F minus N of E and F all over N of S. But you can divide this up, right? Plus minus, that makes it 3 fractions. Right? And all this is the probability of E or F. Right? But number of ways E can happen divided by number of things that can happen, that's the probability that E can happen. This is the probability that F can happen, minus the probability that they happen together. So going back to symbols, the addition principle for probabilities is really the same as it was for counting things, except everything's a probability instead. The complement and probability. Again, we set S, that's our sample space, that's all possible things that can happen. E is some event, it's some subset of things that can happen. Now, what do we know about complements? Well, E union E prime is all possible outcomes, right? Every event, everything that can happen either is part of E or it's not part of E. Everything in S is either part of E or it's not part of E. So E union E prime equals S, and E intersection E prime equals the empty set. There's nothing that's both in E and not in E at the same time. So applying our addition principle for probabilities, we know that the probability of E union E prime is the probability of E plus the probability of E prime minus the probability of E intersection E prime. But we know this, E union E prime, that's just S. So the probability of S is the probability of E plus the probability of E prime. And we know this is the empty set. There's nothing actually in E intersection E prime, so the probability of picking something that's both in E and E prime is 0. But what's the probability of S? What's the probability of picking something that happens? Well, S is everything that can possibly happen, so that probability is 1. So the probability of an event plus the probability of its complement equals 1. And we'll see a bunch of applications of that because you can shorten the calculations needed if you calculate the complement rather than the probability. So that's the two basic things that we'll be working on in this section. The addition principle for probabilities and complements. Okay, so, oh, there was an example here, wasn't there? Yes. So, example, this is much like problems 25 and 26, as I'm sure everybody is well aware, because I hope everybody's a baseball fan, and at least I am. Suppose the probability that the Red Sox win the World Series is 0.7. Just saying. Of course, the probability the Red Sox will win is 100% because the Red Sox are the best team in baseball, especially for those of us who were born in Boston. But so the probability the Red Sox win, suppose that's 0.7. What's the complement to that? What's the probability that the Red Sox lose? So these are complements because either the Red Sox win or they lose. Those are the two outcomes. So what's the probability the Red Sox lose? Well, 1 minus 0.7, which equals 0.3. And so that's an example of using a complement to calculate something. To calculate a probability, right? If you know that the probability the Red Sox win is 0.7, then the probability that they lose must be 0.3. Okay, so let's go back to some Venn diagrams. And probability. Right, and problems 1 through 6 and 71 through 74. Oops. And 71 through 74 are a lot like this. So, I'm not going to actually give a setup for this. I'm just going to draw a Venn diagram. So suppose you have some problem that asks you to draw a Venn diagram, and you draw the Venn diagram. Here's our traditional Venn diagram. Remember, when you're doing Venn diagrams, include the box. The box represents the sample space S. And one circle is A, and one circle is B. And suppose you get this distribution of things. So N of S here is 30. There's 30 things total if you add them all up. N of A is 15, N of B is 20. So what is the probability, if you pick one of these 30 things, what's the probability that it's in A or B? Remember, union means A or B. Well, we can actually count that here. Right? There's 27 things out of 30 total. That's 0.9. So if you're going to pick something at random out of this entire set, right, you've got a 90% chance of picking something either in A or in B. Right? There's only 3 things that are outside of that. But you can also use the addition principle for this. Probability of A union B equals probability of A plus probability of B. Oops, that should be a B and not some kind of weird heart thing. Minus the probability of A intersection B. So, what's the probability of A? Well, there's 15 things in A out of 30. And there are 20 things in B out of 30. How many things are both in A and, that's what the intersection stands for, and in B? Well, that's 8. There's 8 things in the circle for A that are also in the circle for B. So minus 8 out of 30. If you combine that into one thing, you get 35 minus 8, 27 out of 30, which is 0.9, as we got before. So that's the probability of A union B. Great. So what's the probability of picking something not in A or in B? Well, in A or in B, this is A union B. Not in A or B, the not means that I'm looking for the complement. So this is asking for the complement. What's the probability of picking something that's not in A or B? Well, we know that the probability of picking something in A or B plus the probability of picking something in the complement of A or B equals 1, right? The probability of something plus the probability of its complement has to be 1. We know this is 27 over 30. We don't know what this is, or at least we're pretending we don't know what this is. So what's the probability of A union B prime? 1 minus 27 over 30. 1, of course, is 30 over 30, so this is 3 over 30, which is 0.1. Not a big surprise, right? If the probability of A union B is 0.9, then the probability of A union B prime has to be 0.1, because either something is in A union B or it's not. If you look at the Venn diagram, there's 27 things in A union B and 3 that are not, so the probability of picking something that's not in A union B is 3 out of 30. So there's a little Venn diagram and probability thing in complements. So Venn diagrams, you know, once you realize which section you're dealing with and how many things you have total, right? The probability is the number of things that you're interested in the regions that you're interested in divided by the total number of things. Okay. Card problems. Right. And this is problems 7 through 18 in 8.2 and 53 through 56. There are really 2 types of problems they have here. 7 through 18, you draw 1 card at random from a standard deck of 52. So, what are all the possible outcomes that you can get if you pick 1 card at random? Well, you can get any 1 card. How many cards are there? There are 52. So n of s is 52. And that's always the denominator when you're picking 1 card at random. Denominator from a deck of 52. Okay, so suppose we have 2 events. H, drawing a heart. And there are 13 hearts. And N is drawing a number card. right? And so this would be 2 through 10 of any suit. And this is, well, there are 13 hearts. So how many number cards are there? Well, there's 9 in each suit. There's 4 suits, so there's 36 total. N of H equals 13. N of capital N equals 36. So, again, we can say, what's the probability of N union H? What is this? Drawing either a number card or a heart. What's the probability of that? Well, it's the probability of N plus the probability of H minus the probability of N intersection H, because that's our addition principle again. And this, drawing a card that is both a number card and a heart. Drawing a card that is both a number card and a heart. Right? So notice the difference here, right? This is a number card and a heart. This is either one, right? So this is drawing a card that's a number, so like the 2 of spades, or a card that's a heart, like the king of hearts. Here, drawing a card that is both a number card and a heart, that means like the 2 of hearts, or the 3 of hearts, the 4 of hearts. So what's our probabilities here? Probability of N union H, we don't know what that is, but we know how many number cards there are. There's 36 out of the 52 we've got. Probability of drawing a heart, we know there's 13 out of the 52 we got. How many cards are both number cards and hearts? Well, there's 9 number cards in each suit, right? 2 through 10, so minus 9 over 52. And that's 40 over 52, right? 49 minus 9 is 40. And that's 0.7692 if you multiply all that out. Okay, so that's number cards or hearts. You can also calculate this directly. Right? By saying, well, how many number cards are there? There are 36 number cards plus king, queen, jack, ace of hearts. And that covers all the number cards and all the hearts, because the 2, 3, 4, 5, 6, 7, 8, 9, 10 of hearts are already counted here. So it's 40 equals 40 out of 52, which is what we expected from up there. Okay. Now, so a bunch of these problems, I think 53 through 56, deal with drawing multiple cards. Right? And these are like the poker hand problems, so this is 53 through 56. And a particular example we'll do is, suppose you draw 7 cards at random from a deck. And what's the probability of at least one card, one face card? At least one face card. Okay, so what does at least one face card mean? Well, if you draw 7 cards, how many face cards can you get? The possibilities are 0 face cards, 1 face card, 2 face card, 3 face cards, 4 face cards, 5 face cards, 6 face cards, 7 face cards. That's really the options here, right? You've got to have somewhere between 0 and 7 face cards when you pick the 7 cards at random. So this is the event at least one face card. And so we'll call that E. So to calculate this directly, right, I have to calculate what's the probability of getting exactly 1, what's the probability of getting exactly 2, what's the probability of getting exactly 3, 4, 5, 6, 7, and then add those all up. This, however, if this is all E, this must be the complement to E, E prime. And that's exactly 0 face cards. So, calculating the probability of E is tedious because I have to do 1, 2, 3, 4, 5, 6, 7 calculations. Calculating the probability of E prime is pretty straightforward because I just have one calculation to do. So, what do I know about the probability of E and the probability of E prime? Well, the probability of E prime, 1 minus the probability of E prime, gives me the probability of E. And what's that? Well, how many cards am I picking? I'm picking 7 out of all 52. So C52, 7, that's my sample space. That's the size of my sample space because I'm looking at all 7 card hands. And no face cards. Well, I need to pick 7 cards that are not face cards. How many cards are not face cards? 40. Right. So, where does this come from? Pick 7 cards from 52, all possible outcomes. So that's all possible 7 card selections, all possible 7 card hands. And then 12 face cards. So 40 cards not face cards. What's the desired number of outcomes that we want? We want cards, 7 cards that are not face cards, so we choose 7 of 40. And that gives me that. And then if you do the calculation, this turns out to be 1 minus 0.1394 equals, this is all the probability of E, the probability of getting at least 1 face card. The probability of getting no face cards is about 13.94%, so the probability of getting at least 1 is 0.8606. So if you pick 7 cards at random from a deck of cards, you've got an 86% chance of picking at least 1 face card. So words like at least or at most are often tied to complements, because sometimes it's easier to calculate the complement and then subtract it from 1 rather than calculate all the possible events that go into the one particular event that you're looking for. Okay. Rolling 2 dice. This is problems 27 through 30. Well, I'm not going to fill out the whole table, but we know there's 36 outcomes. Right? Because what's the process of rolling 2 dice? You roll the first die, and you get 6 outcomes for that, and you roll the second die, and there's 6 possible outcomes for that. So rolling 2 dice, there's 36 possibilities. And we know that, just very quickly, the probability of getting a 2 is the same as the probability of getting 12. There's only one way to do that. Probability of getting a 3, that's the same thing as the probability of getting 11. That's 2 ways to do that, a 1 and a 3. 1 on the first die, 3 on the second, and 2 on the second die, or 2 on the first die, 1 on the second die. Probability of 4 is the same thing as probability of 10. That's 3 out of 36. Probability of 5, same as rolling probability of a 9, not a 6. And that's 4 out of 36. Probability of getting a 6 is the same as the probability of getting an 8. That's 5 out of 36. And then the probability of getting a 7 is 6 out of 36. So it goes from 1, 2, 3, 4, 5, 6 as you count your way up from 2 to 7, or as you count your way down from 12 to 7. So what's the probability of getting an odd number or a prime number? Well, again, that's the probability of getting an odd number plus the probability of getting a prime number minus the probability of getting a prime and odd number. Okay, so the odd numbers are 3, 5, 7, 9, and 11. The prime numbers 3, 5, 7, 9, and 11. The prime numbers are the ones that are only divisible by themselves. So that's 2, 3, 5, 7, and 11. So which of these numbers are prime and odd? Well, 3 is in both, 5 is in both, 7 is in both, 11 is in both. So these are 3, 5, 7, and 11. So what's this probability of odd or prime? Well, the probability of an odd number is 3 and 11. Well, probability of getting a 3 is 2 out of 36, plus probability of getting a 5 is 4 out of 36, plus a 7 is 6 out of 36, plus a 9, where's my 9? Is another 4 out of 36, plus 11, which is a 2 out of 36. So that's the probability of getting an odd. What's the probability of getting prime? It's 2, which is a 1 out of 36, plus the 3, which is a 2 out of 36, plus the 5, which is a 4 out of 36, plus 7, where's my 7, which is 6 out of 36, plus 11, which is 2 out of 36. Minus 3, 5, 7, and 11. That's this. So that would be minus 2 out of 36 plus 4 out of 36 plus 6 out of 36 plus 2 out of 36. So note that in doing this, anything that was repeated, right, 2 out of 36, 2 out of 36, 4 out of 36, 6 out of 36, right, those all had to be canceled out because we got them twice. So this and that go away, this and that go away, this and that go away, this and that go away. Great, and so we're left with the probability of odd or prime is 6, 12, 16, 17, 18, 19 out of 36, which is 0.4167 if you calculate that out. So note that the probability of getting a prime number is odd and prime. That should be 19 out of 36. Did I screw up my numbers? Probability of odd is 18 plus 1. It should be 19 out of 36. Yeah, that's 19 out of 36. Probability of a prime number, though, is 10, 12, 14, 15 out of 36. So what's the probability of a not prime number? Well, a number is either prime or not prime. If you've got 15 out of 36 chances to get a prime number, you must get 21 out of 36 ways to get a not prime number. Right? And again, the probability of a complement plus the thing itself have to add up to the total number, have to add up to 1. The probabilities have to add up to 1. Okay. And last example is a quality control problem. This is like problem 75 and 76. So, a shipment of 13 dozen donuts that's 13 dozen are shipped out. So the shipment went out, but 8 were defective. And in this context, since I'm making up these problems, being defective means that they had coconut in them. Of course, this is a little lighthearted thing about donuts, but people do have severe fruit allergies, right? So if you had 156 donuts that went out and you said, these are peanut-free donuts, but 8 actually contained peanuts, then you might have a serious problem, and you need to do some kind of quality control to make sure that you're not shipping out contaminated things. So what's their quality control procedure? So for quality control, what they do is pick a dozen at random, at random and test for coconut. Period. If any in the sample are defective, then you cancel the shipment and say, okay, we've got a problem in our plant. We're shipping out donuts that are contaminated with coconut. There's some kind of cross-contamination problem. We need to find it. Right? So this is a very standard thing in a lot of businesses, is doing some kind of quality control like this. So any in the sample, what does that mean? Well, that's the same thing as saying at least one in the sample is defective. And as we've seen before, at least one can be a complicated thing. Here, at least one means either 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. Calculating the probability that you got that many in the sample is tedious, doing all of those. So complement to this is none in the sample, right? Because either there are no contaminated ones or there's at least one. Those are our complements. This is actually easier to calculate. What's the probability if we set E to be at least 1 is contaminated, then E prime is exactly none. Exactly none are contaminated. Great. So, how can we calculate that? Well, how many samples can there be with no contaminated donuts? Well, we're picking 12 donuts. What is that? Pick a dozen at random. Out of, well, how many are non-coconut infested? Well, there's 148. 156 minus 8 have no coconuts in them. So we're going to pick, out of the 148 good donuts, we pick 8. So that's n of E prime. So what's the probability of E prime? Well, the numerator will be C 148, 8. And the denominator is how many possible choices of... God, I'm sorry. We're picking 12 out of 148. How many possible choices are there of samples, right? 156 donuts, we want to pick 12 of them. So C148 over 12 over C156, 12 is 0.519. So the probability of picking a set of 12 donuts out of the 148 that are clean is, well, 51.9% of all samples are completely clean. So what's the probability of having at least one contaminated donut? Well, that's 1 minus P of E prime, and that is 1 minus 0.519, which is 0.4810. Right? So a 48% chance of getting at least one contaminated donut. There's a 48% chance that this particular quality control system with this particular distribution of numbers will actually catch that some of the coconuts are defective. Of course, in real life, right, things are much more complicated, and particularly you don't know how many are actually defective. But, you know, this is the basic idea of a bunch of quality controls. So, as we've seen in a couple of different places here, we have complements, right? Probability of prime and not prime. Probability of prime plus the probability of not prime, that has to add up to 1. And so we can calculate a complement, sometimes easier than calculating the original thing. So here's a good complement problem. And then we have the probability, the addition principle for probability. We just add the probabilities and subtract off the overlap. It's exactly the same as the addition principle for counting things, except everything is a probability. So Rule for complements.